and now we'll be covering the house as a system. So what is a system? A system is a set of interacting or interdependent components forming an integrated whole. A system has three things. So it has a structure, which contains parts or components that are directly or indirectly related to each other. It has a behavior, which contains processes that transforms into inputs into outputs. So in our particular scenario, for example, energy, right? And they have interconnectivity. So the parts and processes are connected by structural and or behavioral relationships. So basically, each building component into in a house interacts in some way with the other building components within that particular structure. So what are the building components of the house? We have the building envelope, space conditioning, lighting and appliances, mechanical ventilation, water heating and distribution, and obviously the occupants as well. Homeowner behavior will interact differently with how the other components of the house itself and how they were built. So the house is a system made up of interdependent parts, which I just listed a second ago. The operation of one part affects many others. So for example, the insulation and the quality of the insulation will affect how the air conditioning system works. Poor insulation will make the system work harder, for example, right? That's a very easy example. When all parts work together, the house is comfortable, safe, efficient, and durable. A house will experience problems when its components do not work in unison. So the problems that can arise from components in a house that don't work properly together can range from just high energy bills. They can result in just inefficiency, discomfort, and in some scenarios can also produce life-threatening scenarios, which we'll talk about in a minute. So for example, let's talk about some interconnectivity issues, right? So an attic without insulation makes the heating and cooling system work harder than necessary. So this will decrease the HVAC equipment's life and cause higher than necessary energy bills. So let's say in the winter, again, you're heating up your house, there is no insulation in the attic, that hot air will just rise up and it will leak out, right? It will transfer right out. So your heating system will work probably twice as hard as it should. Therefore, your energy bill is going to be higher. The life of your equipment is not going to be as long as it should because it's going to be working much harder than it's supposed to. So that's an example of two systems not working properly together. Another example, you have leaky recessed lighting fixtures, and you see pictures here with thermal camera. Increase heat loss and gain. So please note on the right hand side, the hot roof in the picture on the right, the hot air rising through leaks around the can light deposits in the attic. Again, so that goes with heat losses, right? So the heat inside the house is leaking through the poorly sealed can lights, and it's heating up in the attic. So you can see in the picture on the right hand side, you'll see the roof that's bright red, right? So that means that the attic is hot. So assuming that's a non-lived-in attic, that attic should be cold because it should be completely insulated from the inside of the house. This is an example of mechanical ventilation not exhausting properly to the outdoors, which can cause moisture damage to the roof deck and trusses. So moisture in this particular case will deposit and condense on the underside of the roof, causing it to rot over time. So basically, any kind of you have any kind of mechanical ventilation exhausting from the house, it needs to exhaust completely outside of the structure, not just into the attic. So basically, in this particular scenario, you have mechanical ventilation that's exhausting hot air from the inside of the house. Now think of the fact that the attic is going to be colder, right? So as hot air reaches the cold attic, the hot air is going to condense and moisture is going to form in the area around that vent in the attic. And that moisture eventually is going to be absorbed by the building materials, and it's going to create rot and moisture problems down the line. So those are just examples of it, but basically everything in the house interacts with one another. So you can't insulate unless you air seal, right? So because air sealing is basically pressure boundary, insulation is thermal boundary, like we mentioned earlier. If you insulate without air seal, you don't have the pressure boundary, thermal boundary connection, so you cannot do one without the other. You can't air seal unless you insulate. If you stop the pressure boundary, but you don't put a thermal boundary in there, now you stopped air movement, but now you're not going to stop heat flow, right? You can't air seal unless you have combustion air. So combustion air is basically the air necessary for a combustion appliance to burn properly. If you air seal but don't provide any kind of makeup air for your combustion appliances are not going to work properly, and they're going to create CO, which is a dangerous chemical, which we'll talk about in a sec. And then you have to test for combustion after you air seal. So every time you air seal a house and you basically tighten it up, the pressure boundary of the house is now much tighter. There's the potential of a dangerous situation being created with your combustion appliances. So it's important that you test for combustion air after air seal. So basically you have to make sure that there's enough makeup air for those combustion appliances to work properly. Now, as you can see, everything works with one another. You cannot do each one of these things interdependently. You have to take everything else into account. If you don't, again, you might have energy problems, you might have comfort problems, you might create actual damage to your structure due to moisture and so forth, or you could create dangerous situations just like the production of CO, which can kill you. So like I said, when the house does not work as a system, problems will occur. Insulating and venting the attic without air sealing could damage the roof, like we mentioned. Air sealing without insulation could cause moisture problems. Air sealing and insulating without attention to the HVAC ducts will not reduce duct leakage. So for example, you air seal and insulate your walls, but now your ducts are still leaking like a sieve. Obviously, that's still going to be very inefficient. And then air sealing without combustion safety testing will cause a hazardous and potentially fatal situation for the residents. Not knowing the status of the air tightness of the house in relation to the combustion appliance present, it's a danger on its own. So it's not necessarily that it's going to happen, but the reality of the fact is that it might happen. And not knowing whether it does or not is dangerous on its own. Anytime you air seal, you absolutely should test the house to make sure that the combustion appliances are working properly with the new air sealing. And these are additional examples. So insulating and venting an attic without air sealing could cause moisture damage on the roof. So if you're not air sealing, it means that you're stopping heat transfer, but not air movement. So the hot air rising from the house will condense and potentially freeze on the underside of the roof, causing damage to the roof and allow moisture to fall back on the insulation and below. So you have hot air that rises in the attic. Once it touches the cold roof deck, it condenses. Therefore, once it condenses, it might freeze depending on the temperature on the outside. Eventually, it'll melt. It'll cause damage to the roof deck, plus the moisture will fall back on the insulation. So it's a chain reaction effect that can cause multiple problems. Also, keep in mind that the problems that you may encounter vary from climate zone to climate zone. So the problems you're going to encounter in a hot climate zone are going to be different than the problems you encounter in a cold climate zone. So another example, air sealing without insulating could cause moisture damage. So heat transfer will cause condensation to build within the walls once the outside air touches the inside surface, or vice versa, thus causing moisture to form in the wall cavity or on the walls. So basically, you have a wall that's properly sealed for air movement, but there is no insulation in there. So what's going to happen is you're still going to have heat transfer coming in from the outside or the inside, depending what's going on. And because there is nowhere for that air to go, because it's sealed, that air is going to be trapped within the cavity. And due to the temperature differences, it might condensate. If it condensates and becomes actually moisture, then at that point it'll deposit on the inside of the walls and start causing moisture problems from the inside out. And as you can see here, it's an example of a wall that's rotting, and there was moisture being built, could be from the inside, due to that. Air sealing and insulating without attention to the HVAC will not reduce duct leakage. So obviously improving the thermal and pressure boundaries of a home will not solve the energy loss associated with the leakage of the HVAC ducts and the moisture problems associated with it. So again, you could have a perfectly built house on the outside as far as the walls, ceiling, raised floor, and then you have an air conditioning system that's leaking completely. And basically if it's leaking, it's going to be sucking air in or out of the outside of the home, because that's where the ducts most likely will be. So you got to also pay attention to the duct sealing on top of that. Air sealing without combustion safety testing, that can potentially kill somebody. So like I mentioned earlier, air sealing may cause combustion appliances not to vent properly, thus causing backdrafting and forcing CO inside the house rather than letting it flow outside. CO is a very dangerous chemical and it can kill somebody. So that's what CO is. So it's a colorless, odorless, tasteless gas. It's highly toxic. It's a byproduct of improper combustion. So if combustion appliances don't have enough oxygen to breathe properly, they produce CO. And CO can cause a range of symptoms depending on exposure levels, for anywhere from a headache all the way to death. So if there's CO exposure within the home, a lot of the low level exposures of CO are actually flu-like symptoms. Now you cannot smell CO, you cannot see CO, you cannot taste CO. So a lot of times you might be in a dangerous situation where you think that you might just have a flu or you just don't feel good, but the reality of it is the fact that you're breathing in CO because your home is not performing properly. So if the house is very airtight and there is nowhere for CO to draft out, or it's being drafted inside because mechanical ventilation is sucking it in from the appliance, they can cause a very dangerous situations. If you read the news or if you do research, you'll see that around the winter seasons, thousands of people die yearly from CO exposure. It's a very common thing to happen, and it's something that you definitely have to be aware of when performing modifications to the house. Energy and efficiency can be divided into the following general categories. You have heating and cooling. Seasonal efficiency for fossil fuel heating systems range anywhere between 30 to 90%. Most older systems operate at the mid to lower level of the scale. You have air leakages, so infiltrating air must be heated or cooled to a comfortable temperature, and heated or cooled air is lost when air leaks out of the building. You have water heating. Energy losses in heating and storage of hot water can amount up to 40% or so of the system energy consumption. You have appliances and lighting. So refrigerator, lights, entertainment systems, computers, and other appliances, they use considerable electrical energy because of obsolete design, careless operation, or just the sheer number of electrical devices in a home. Think of a number of laptops, tablets, phones, computers, TVs, gaming systems. All those add energy usage to the home. And think of how many electronics we have added to our average homes compared to where we were 10, 20 years ago. And then finally, you have residential behavior. The awareness and care of building residents and managers has a significant influence on how much energy the building uses. So aside from actual, electronics and building design, I mean, the homeowner has a very big impact on the efficiency of the home. If a homeowner leaves all the lights on all the time, obviously they're going to be using a much more, they're going to be having a much higher energy bill than somebody who doesn't. So generally speaking, typical residential buildings use 1.5 to 2 times more energy than necessary, and that's through a combination of the things that I just listed a second ago. Largely, though, is caused by a lack of insulation, infiltration, and improperly installed or inefficient heating and cooling systems. So this excess energy usage costs about $45 billion annually to the U.S. So think of all that energy and efficiency and how much that translates to that 45 billion. That's quite a number. So achieving maximum energy efficiency can be reached through the use of two methods, and these are the ones that we're going to be talking about. We have energy efficiency strategies, which is using devices that draw less energy, often resulting in energy savings. And then you have energy conservation strategies, changing individual habits to reduce energy use. So energy efficiency is the more popular approach and focuses on maximizing the economic benefits of wise energy use. Energy efficiency often results in energy savings, as when you buy a new energy efficiency star qualified refrigerator to replace your inefficient old one. So basically, energy efficiency strategies really have to do with improvements of the home. Now, energy conservation focuses more narrowly on reducing now renewable energy use and its resulting environmental damage. Proponents of this approach are more willing to ask consumers for changes in behavior than than the energy efficiency approach. So energy conservation is more behavior focused versus the energy efficiency, which is more building component upgrade focused. So these are examples of energy efficiency strategies. So making thermal improvements to the shell, replacing older heating and cooling systems with newer, more efficient ones, installing smart strips to appliances, or replacing incandescent light bulbs with CFLs or LEDs. Now, as far as conservation strategies, these are other examples. Unplugging appliances when not in use, not cooking during the heat of the day, using clotheslines instead of dryers, or programming the thermostat properly so that it's preset at certain temperatures and times. So again, you can see these are more behavior-based versus upgrade-based that we saw in energy efficiency strategies. So how does building science relate to actual human comfort? Now, there are different factors that determine personal comfort. You have air temperature, you have relative humidity, you have air movement, you have mean radiant temperature, and then you also have the individual itself. Now, we mentioned a second ago air temperature, and we talked about, well, I mentioned relative humidity. So those are examples of sensible and latent heat. So what do they mean? Heat obviously has to do with personal comfort. It's a big factor in it. So sensible heat, it's heat that causes a change in temperature in an object. So that's a very easy example of air temperature, right? Latent heat is heat that causes a change of state, like solid to liquid or liquid to vapor, with no actual change in temperature. So relative humidity is an example of latent heat. So we talked about air temperature. So basically, it's very easy to measure with a thermometer, for example, right? It's the measure of how hot or cold the air is. It describes the kinetic energy of the gases that make up air. And as the temperature increases, air molecules move more quickly. As it decreases, they slow down. Hence, they turn into a vapor or they condense down to moisture and then down to a liquid. Now, relative humidity is the ratio of amount of water in the air relative to the amount of water that air can hold and its current temperature. So warm air can carry more moisture than cold air because it becomes less dense when heated. So as it becomes less dense, the molecules expand, hence allowing it to hold more moisture. So 100% relative humidity is completely saturated air. So at 100% relative humidity, it's basically raining, right? That's what 100% relative humidity is. Healthy levels are between 40 and 60%. And this is the chart that shows that. So when it comes to humidity, there is health factors and problems that can vary whether it's too dry or it's too moist. And you can see here the range of what those problems may be depending on the range of temperature of relative humidity. And as you can see, the safe zone or the hot spot, I guess, is between 40 and 60. That's the healthy range. You're still going to have some problems about some of these items in that range, but nonetheless, they're going to be greatly minimized. The lower or higher you go, the more those problems are going to manifest themselves. And this chart shows the perceived temperature due to relative humidity. So if you have a low temperature, but nonetheless you have high humidity, it's going to feel hotter to the individual than it actually is. So in this particular scenario, I'm just going to use an example. If you look at the column that says 80 Fahrenheit for air temperature, but then you have 70% humidity, now it's going to feel like 85 degrees to the actual individual. And that's how it works. Because of the fact that the temperature is higher, therefore it can hold more moisture. The relative humidity might be higher, and it's going to give a perception of a higher temperature, therefore decreasing the comfort of the individual. So air movement can increase heat loss without any change in actual temperature. So it does increase personal convective heat losses. If the air temperature is less than the skin temperature, it will significantly increase those convective losses. This occurs because more air is coming in contact with the warm skin as it blows past. With little or no air movement, now mean radiant temperature, the measure of the average temperature of all the objects in a space, including the walls, windows, furniture, and people. So it's critical to human comfort because our bodies radiate heat toward cold surrounding surfaces and receive heat from hot surrounding surfaces. So there's about 1 degree change in mean radiant temperature is approximate to 1.5 degrees change in air temperature. So our surroundings affect our comfort level. . And then, of course, the individual. The individual will have an effect on its own comfort based on the physical condition of the individual, the level of activity of the lifestyle, the age, the metabolism, the acclimation, and the gender. So basically, any of these items will affect the comfort of the individual independently from everything else that we just talked about. So everything else could be proper, but these factors will additionally change the comfort of the person. And again, if you have any questions, contact us through the messaging system or give us a call.